So this is joint work with Kyle Hambrook. Although for the most part, what I'm going to be describing today is just sort of a general idea of, first of all, what an algebraic number field is. And then I'm going to describe how we specifically used algebraic number fields to solve one specific problem. But the thing that I want everyone to keep in mind is that I think that this technique will see a lot of applications to other kinds of problems. So just keep an eye out for situations where you think you could use it. So what is an algebraic number field? Well, an algebraic number field is just a finite extension of the rational numbers. So you take the rational numbers, you throw in an additional element, and some algebraic number, like for example, you can look at the cube root of 2, and you look at the field that you get by adjoining that element to the rationals. So for example, this field consists of all of the numbers of the form a0 plus a1 cube root of 2 plus a2 cube root of 4, where a1, or a0, a1, and a2 are rational. So I'm going to go into the algebraic properties of these algebraic number fields first, and then I'm going to discuss a bit why they showed up in the solution to this problem. So algebraic number fields are fields. So they're closed under addition, subtraction, multiplication, and division. And there's a very special subring of an algebraic number field. And I'm going to get into what that is in just a second, but just a quick definition. An algebraic integer is an algebraic number that's the root of a monic polynomial with integer coefficients. So if you look at the set of all of the algebraic integers in an algebraic number field, that set is called the ring of integers of the number field, and it's denoted O of k. So you can view an algebraic number field as a Q vector space because an algebraic number field is a finite extension of the rationals. So if you have an algebraic number field of degree d, when I say degree, that's basically the vector space dimension of k as a Q vector space. So you can talk about bases for this vector space. And there's a very special type of basis that algebraic number fields will always have, and it's called an integral basis. So we call a basis, a vector space basis B for an algebraic number field K, an integral basis if each element of B is an algebraic integer, and each algebraic integer is some integer linear combination of the elements of B. So as it turns out, every algebraic number field will have an integral basis, and this is going to be useful for us. So one other thing that's useful for us is that you can view multiplication as a linear operator. So if you have some element x of your algebraic number field, you can view it as a linear operator on K, where you view K as a Q vector space. So if you fix a basis of K, it allows you to associate an element of your algebraic number field to a matrix with rational entries. And this is important for us because matrices with rational entries are something that you can understand as acting not just on elements of this vector space, but you can view them as acting on vectors in some Euclidean space as well. So this allows us to relate these algebraic number fields to Euclidean problems. And what's nice is that if our basis B that we're choosing turns out to be an integral basis, then the matrix A sub x has integer entries if and only if x is in the ring of integers of K. And if x lies in the ring of integers of K, then the determinant of this matrix is always the same, independent of what the basis is, as long as B is an integral basis. And the determinant is equal to the field norm of x. So there are many different characterizations of the field norm, but the thing that we're going to need is that the absolute value of the field norm is the number of residue classes modulo x. So here's a quick example. Let's suppose that our field is the integer or the rationals adjoin cube root of 2, and we choose the basis 1, cube root of 2, cube root of 4. Then if you multiply two elements of this number field, you get this product here, which I've arranged by putting the square root of 2 terms together and the square root of 4 terms together. And then within each row, I've arranged these by which y it is. So you can just read off the entries of the matrix A sub x just by looking at the coefficients of the y's in each row. So that gives you this matrix, which we associate to the element x0 plus x1 cube root of 2 plus x2 cube root of 4. So that's all I want to say about the algebraic properties of these algebraic number fields. So why did this show up in solving a problem in analysis? Well, one of the most important facts in analysis is orthogonality of characters. So if you have any non-zero integer q and any integer r, then this sum, the sum of e to the minus 2 pi r s over q, as s ranges over all the integers mod q, is equal to q if r is congruent to 0 modulo q and 0 otherwise. And this property actually works just as well if instead of considering integers, you consider the ring of integers in an algebraic number field. So if you let q be in the ring of integers of k, then for any r in the ring of integers of k, you have that the sum over all different s modulo q of e to the 2 pi I r over q is, well, if r is congruent to 0 mod q, then each summand is 1, so you get the number of summands, which is the field norm, with an absolute value, of course. And otherwise, you end up getting 0. So this means that you can often use, or this means that at least for some purposes, you can use the ring of integers of a number field as a sort of multi-dimensional substitute for the integers. So that's all I have to say about number fields. And I'm going to switch gears and talk about the problem that we solved. So Malabika introduced the concept of Fourier dimension in her talks, but I'm just going to briefly go over it again. So the Hausdorff dimension of a set is basically the largest value of S.
So you mean the Malabak, right? Monaco, right?
What did you say?
The Canadian mathematician Malabak defined the Fourier dimensions. So did you just refer to that?
I mean Malabika Promanique.
Oh yeah, yes.
Yeah. She defined Fourier dimension. So I'm just gonna go over the definition again.
Yeah, in her talk.
Yes.
Okay.
Yeah, I meant in her talk she defined it. She didn't.
Yeah,
she didn't introduce it.
Yeah, sure. Yeah.
Thank you. Sorry, that was unclear. I meant in her talk she defined it. So I'm sure everybody in the audience who saw her talk knows what it is. But for those of you who missed her talk, I'm just going to remind people. So Frostman's lemma says that the set E is Hausdorff dimension at least S if and only if E supports a measure whose Fourier transform in an L2 average sense basically decays like c to the minus s over 2. And if you replace this average Fourier decay condition by a pointwise Fourier decay condition, then you get the Fourier dimension. I didn't write the term Fourier dimension, but this is exactly the condition corresponding to the Fourier dimension that Malabika introduced earlier. And so there's the problem of trying to find sets whose Fourier dimension is equal to their Hausdorff dimension. So Malabika gave an example of a random set where she looked at translations of the Behrend example, basically. and that gave her a set of Fourier dimension 1. But the point is that that particular example made a lot of use of a random procedure. So it's very difficult to find explicit examples of sets whose Fourier dimension is equal to their Hausdorff dimension. And by the way, if a set has the same Fourier dimension and Hausdorff dimension, we say it's a Salem set. So the first and most well-known example, explicit example of a Salem set in the real numbers was given by Kaufmann. And Kaufmann showed that the set of tau approximable numbers, so that's the set of real numbers x such that x minus r over q is bounded above by q to the minus tau for infinitely many q and r. Kaufmann showed that for tau greater than 2, this is a Salem set. So this set's only interesting when tau is greater than 2, because if tau is less than or equal to 2, a pigeonholing argument shows you that this is the entire real numbers. So Kaufmann showed in 1981 that this is a Salem set of Hausdorff dimension 2 over tau. So the Fourier dimension is also 2 over tau. So I'm just going to briefly outline one important step of Kaufmann's proof. So Kaufmann uses the orthogonality of characters on the integers. So Kaufmann obtains his measure as a weak limit of essentially uniform measures on sets E sub tau m, where you consider points x that are close to rational numbers whose denominator is close to m. So if you look at the Fourier transform of the uniform measure on this set, and you let xi be an integer, then what ends up happening is that you get a contribution to the Fourier transform of the uniform measure at xi from each different choice of q. And for those q that divide xi, you get a contribution of q. And for those q that do not divide xi, you get a contribution of 0. So this follows directly from the orthogonality of characters. And to get the desired Fourier decay estimate, the only thing that you need to realize is that if you have some xi, you can get an easy estimate on the number of divisors just using the divisor bound. So the idea is that this gives you a good idea of the Fourier transform of the uniform measure of E sub tau m, and then you put this together at a bunch of different scales for a bunch of different m's by using a convolution estimate. So for a long time, it was unknown how to construct explicit examples of Salem sets in dimensions higher than 1. Kyle Hambrook actually did this in 2 dimensions. And then together with Hambrook, we managed to do this in higher dimensions. So what we do is we replace the approximation by rationals appearing in Kaufmann's argument by approximation by elements of some number field k. So what we do is, let's suppose that you let k be a number field of degree n, and let's consider a set of points in Rn such that x is close to AQ inverse R, where AQ is the matrix we introduced earlier. It's the matrix corresponding to the element Q of the ring of integers of k in the basis B. So if you look at those real vectors x that are close to this matrix product, again, this is R is an integer vector and AQ inverse is a rational matrix. So it makes sense to say that AQ inverse R is close to a real vector. If you look at those vectors x, then you can see that this is a Salem set. And again, the proof is similar to that of Kaufmann. There are a few differences that are very technical in nature, but fundamentally what you do is you again look at sort of a finite approximation to your set, where you look at just those x that are close to AQ inverse R for some q of size close to m. And again, you use the orthogonality of characters to show that essentially the only values of Q that end up contributing to the Fourier transform of the uniform measure will be those values of Q such that AQ inverse transpose C is an integer vector. So making sense of this transpose took a bit of work, but it essentially just amounts to a change of basis. So this condition that this product is an integer vector is related to, but not quite equivalent to, the condition that Q divides C in this ring of integers. And then from here, what you do is you use a divisor bound for the ring of integers of K, and that gives you the desired Fourier decay estimate on your measure. So I guess I'm just going to end by saying that I think that there are lots of problems in harmonic analysis where you sort of get an advantage by equipping, say, the reals or R2 with a multiplicative structure. So often on the reals, you'll just want to consider the usual multiplication. And for R2, you often want to give it the structure of the complex numbers and take advantage of complex multiplication. So I guess that what I want to say is that even though you don't get a field when you do this, you can sort of equip Rn with a multiplication operation that you sort of get by completing these algebraic number fields with respect to the usual Euclidean topology. And I think that if you consider this multiplication operation, I'm hoping that this will extend a lot of tricks that work in 1 or 2 dimensions to higher dimensions. It's just sort of a thing to think about, I guess. So I guess I'll end with a picture. These are just some pictures of some of the Solem sets that we considered. And thank you so much for your attention.